Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 8th, 2026, about 4 days ago. It identifies a critical memory wall in AI hardware, pointing out that while GPU compute has jumped 80 times in a decade, memory bandwidth has only grown 17 times, leading to a proposal for radical new architectures like high-bandwidth flash. The paper is titled, Challenges and Research Directions for Large Language Model Inference Hardware. And as we'll see later, the specific solutions they propose could fundamentally change how we build data centers for the next generation of models. To understand the hardware bottleneck, Figure 1 breaks down the inference process into two phases. On the left, the prefill stage processes the user's prompt all at once, which is parallel and computationally dense. However, the process then shifts to the decode stage on the right, where the model generates the response one word at a time. Crucially, the blue bar at the top represents the key value cache. This component stores context to prevent recomputation, but constantly reading from this large memory block for each new token creates the massive bandwidth strain the authors identify. So, to understand the hardware evolution driving this bottleneck, Table 1 details 6 generations of high bandwidth memory, or HBM. The columns track progress from the original HBM in 2013 all the way to HBM4, which is expected in 2026. Looking at the stack bandwidth row, performance has jumped from 128 gigabytes per second to over 2,000. Likewise, the max stack capacity row shows an increase from just 4 gigabytes to 64 per stack. Finally, the bottom rows map these memory standards to famous NVIDIA GPUs, tracing the lineage from the Volta V100 to the future Rubin R100. While the table listed the specs, Figure 2 visualizes the physical architecture that makes those numbers possible. On the left, the top-down view shows the central green ASIC, the main compute engine, tightly surrounded by 4 yellow high-bandwidth memory stacks. They sit together on a silicon interposer, which provides the dense electrical connections needed for speed. Then, the side view on the right reveals the vertical dimension. As the callout bubble highlights, each memory stack is actually a tower of multiple DRAM dies layered on top of a base die, essentially building a skyscraper of memory to maximize capacity within a tiny footprint. Now, Figure 3 reveals the economic impact of that complex engineering. The top chart tracks the cost for HBM3E specifically, where we see a troubling trend. Both the price per gigabyte of capacity, in blue, and the price per unit of bandwidth, in red, have steadily increased over the last 2 years. In sharp contrast, the bottom chart shows standard DDR4 memory, where costs for both capacity and bandwidth generally trend downward. This widening price gap illustrates why relying solely on high-bandwidth memory is becoming an unsustainable strategy for scaling up inference hardware. Alright, given those rising costs, Table 2 maps exactly which AI workloads are hitting these hardware limits. In the top section, which lists the drivers of improvement, notice the heavy concentration of checkmarks under memory capacity, memory bandwidth, and interconnect latency. Whether it is mixture of experts, reasoning models, or RAG, the bottleneck is almost always moving data, not processing it. The single exception is the diffusion row, which remains compute-bound. So, the bottom section proposes 4 research directions, such as high-bandwidth flash and near-memory compute, that specifically target these memory and communication hurdles instead of just chasing higher flops. Well, Figure 4 visualizes exactly how these new architectures would look physically. On the left, Panel A contrasts a standard HBM stack with the proposed high-bandwidth flash. By replacing the yellow DRAM dies with orange flash dies, the system can achieve 10 times the storage density in the same footprint. Then, on the right, Panel B illustrates 3D compute logic stacking. Here, the memory dies are stacked directly on top of the green compute ASIC, rather than sitting beside it on an interposer, which minimizes the distance data must travel. So, while Figure 4 sketched the concept, Table 3 puts hard numbers to the promise of high-bandwidth flash. In the highlighted top row, a single HBF stack offers 512 gigabytes of capacity, vastly outperforming the 48 gigabytes of the HBM4 stack in the second row. Crucially, the flash stack still matches the memory's bandwidth. The trade-off appears on the far right. Read latency spikes into the thousands of nanoseconds, and write endurance is low, which limits this technology to reading static data. Wrapping up, 2 main points stand out. First, the memory wall is the defining crisis for modern AI inference. Second, solving it requires a fundamental shift in hardware design, prioritizing memory bandwidth and capacity over raw compute speed to keep costs sustainable. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.